Итак, уважаемые коллеги, давайте продолжим нашу конференцию. Следующая часть ее посвящена мостам. И я надеюсь, все успели подкрепиться. Но тот, кто не успел, на самом деле кофе-брейк не за горами. Следующий он будет в 13:30. Итак, наш коллега из компании SOFiSTiK, руководитель по менеджменту, развитию программы маркетинга Stefan Maly. Пожалуйста, Стефан.
Yes, now it's working, sorry. So I try to make this presentation sitting because maybe it's then better for you to see my face and also for the video. So my presentation will be a little bit more about the technical background of bridge calculations, mainly in SOFiSTiK. So I will try to explain some of the backgrounds, mostly also features of our CABD, so our axis-based bridge design concept. And so my talk will start with giving you an overview about computer-aided bridge design, CABD. So I will introduce the different components. Then I will try to show you a case study, so a real project. Actually, this was the first project where the CABD technology was applied. Furthermore, if we have time, I would like to show you some reference projects. And maybe if we have some minutes after the talk, we can discuss a little bit and have some questions. And that's also the reason why I asked Dimitri Yaroshutin to stay with me here at the desk, because my Russian is not so good, so he might be able to help me if there are technical questions directly in Russian. So, yeah, computer-aided bridge design, what does it mean? Of course, being a bridge engineer, as Professor Hugo Corres introduced, it's important to understand and to know in advance what your results are, and the software is only a tool. So in order to reduce the complexity, the sheer complexity of the tool, it's better to focus or to reduce the input, especially of the geometry, to be parametric and to be linked to elements which might be used to define the geometry of the bridge. So in order to simplify the input and also in order to simplify the case studies of variations. So if we think about studying different cross-section heights by optimizing a design of a bridge, by maybe optimizing the steel plate thicknesses, but it's more seldom to change the shape and the alignment of the geometry. So in older times, the input of bridge projects was very much governed by a huge amount of work using Excel sheets or interpolations or just hand calculations in order to generate all kinds of different cross-sections, all variabilities in order to generate the bridge, and it took weeks before the first insight or the first answer could be taken from the project. So our CABD, computer-aided bridge design technology, uses the most important geometric descriptions, and here on the slide you see the important elements. So one very important bridge element, which is the main element, is the bridge main axis. So it runs in the middle, and you can relate all your input to this bridge axis. So your first parametric element you will generate is an axis. Then you might have what we call secondary axis. You see this denoted by axis A and axis B, and they can have a constant offset, a variable offset towards this bridge axis. And if you think about a bridge being maybe in not a simple arc radius alignment, but maybe intermediate element, like I would call a spiral element or glothoid element, where you have a maybe constant change of curvature, then it's very difficult to construct and to generate the geometry of a constant offset. You will understand this, because having a radius, an offset of 3 meters, is just increasing the radius by 3 meters. But having a spiral element, it's not that easy to maybe generate dependent elements. And if we think about, we want to model transverse girder at one of the support conditions or one of the support situations, we need to go through a really complex process of sine, cosine, tangent operations in order to arrive at our points, which might be easily described like this. You are at the bridge axis, station 30 meters. Then you rotate around the local bridge axis by 30 degrees or whatever cone, and then you move 3 meters parallel to this axis, and you will obtain a point, maybe this construction or structural point 1110, without any additional hand calculations and additional source for errors regarding the geometry, so we can focus on modeling. So this is the most important thing. The first thing you might model for your bridge, no matter whether it's a beam model or a shell model, will be these axes with the different notions. Maybe one thing I should introduce, that we call this section here, this intersection, which I call support axis, we call placement. So we just say there are placements, point of interest along the bridge axis. So a simple idea would be for a simple 2-span bridge, you might have 3 placements, which are the 2 abutments and 1 intermediate support, right? Then we have a little bit more overview about the different technology or about the different workflows. So when we start to model the bridge, as I said, we start with the geometry, the definition of the axis. So probably you have one axis, probably you have more axes, like the secondary axis, which somehow relate to the first one. Then you might define placement, so important support points. What else could be a placement? A construction joint, auxiliary support point, or whatever you like. So everything which is a section on your bridge axis should be declared as being a placement. Very important placements are these construction joints, because then you build the model for the later construction stage analysis. There are different tools, again, to model this parametric bridge model. So we would start with maybe something like a graphical input of the general road alignment, the axis, using a graphical task, using the mesh generators, or we might be working with a pure DWG, so Autodesk, AutoCAD-based input. So we might be using our graphical cross-section editor to input what we call the master cross-section. You will see later what variabilities can be introduced in the cross-section in order to help you interpolating a cross-section with varying height. Then we might think about the substructure, so maybe having some abutment walls, some piers, some foundations below this bridge axis, so we might add them. I don't want to go too much into the technical detail. I think later on, or in the break, if you're interested in seeing a little bit more, you might be asking my friend Dimitri, or you approach me and we can explain a little bit more about the technical details. After having the bridge model, so we might think about having supports, superstructure, and we have decided for maybe a shell model or a beam model. Then we should think about, if it's a reinforced or pre-stressed concrete bridge, to add the tendon layout or more than one tendon layout. So we might also, and can also relate the tendon geometry, like for example this simple parabolic or Girland-shaped tendons, to the bridge axis. So you don't have to think about any variations which are due to the curvature of the bridge. You just make this input on, so to speak, flat enrollment of the bridge. Then, of course, load analysis or load definition is very important. So we will also be able to relate the loads, the predefined load trains probably, or simple loading directly to these axes. So you don't have to construct these loadings in complex geometry. And I will show this a little bit later on the specific project. And of course, then you might be preparing your construction stage analysis. So you might declare several stages of the bridge to be constructed at a different time. We will see this later on in the practical project. We do have graphical task for inputting this stage analysis preparation, and we do also have text facilities for that. Below you see a little picture of a result envelope of an incremental launching bridge. We will see that bridge in a second later. Then, of course, at the end, if everything worked out well, or if the results are as you expected or as you have pre-calculated, which is usually not so easy, you might be doing your design code checks like ultimate limit state, some detailed things, maybe advanced things like fatigue, earthquake, or any rolling stock, high-speed rail dynamic stuff. And then you will go ahead and document your results. So for example, cross-sectional stresses and forces or results, or here simple stress results on top of the beam, just in order to see whether in serviceability you have everything under compression, the classical decompression condition we have to maintain. Some more advanced stuff, so thinking about going away from a standard beam bridge or a standard shell bridge. I picked two examples. One, of course, because here in Russia I get often asked how about the Russian load trains and Russian specific applications of SOFiSTiK software. As you know that SOFiSTiK has this text input facility for all features, we might simply take one of these input examples and input one of those special trucks which you require, and those load conditions can be used for load stepping, so simple evaluation, and also for influence line evaluation. So you might just simply pick one of our input examples and adopt it to different load trains, maybe not even the Russian trains you need, so you need something else, you might be inputting this manually. And the other thing here is just a detail to show what else can be done. So sometimes you not only need, or you not only can do everything on a global beam model, but you need a more detailed shell model for some intersection. And we see here a detailed model where we use one part of the bridge and remodeled it as a shell model because it's a very wide deck, and it has also leaving lane, so two lanes leave the deck to the left and to the right. And so there was a shell model, and this model was generated also using the axis concept, but we have a lot of different axes because we have one main axis which is straight and two additional main axes to model these exiting lanes, and all these lanes have some secondary axes. Big advantage is that you don't have to construct and don't have to build the model using complicated description of the geometry. Of course, you might say, I could also have input this directly as a DWG and draw it in a CAD model. Of course, this is also possible, sure. Then I come to a case study, so a little reference project. I already introduced this at one of the IQPC conferences, British Russia, I think with Robert together some 2 years ago. And it's another project where also our colleagues from SSF engineers were involved. So I would add another reference project for them in the bridge section. Why I present this bridge is because it was the first application of the computer-aided bridge design, so the axis-based design concept, and during the checking phase of this bridge. So as you might know that in Germany we require a definitive checking of all bridge projects, so it's mandatory to have a second engineer which is specifically capable of checking things, especially if the railway is included. So there is always at least 2 engineering consultants looking at bridge projects. And so in this case, and you see the companies involved in that, so that was, for example, Obermeier for the tender design, then colleagues of SSF did the execution design, the general design and execution management, and the checking was done by Dr. Walter Streit from Büchting and Streit Engineers. And the good thing is that for the checking, you are supposed to choose a different model, because it doesn't make sense that you do the same calculation again, or at least it is better to try to have a different model. Sometimes it's not really possible because maybe it's the best way to use beam elements, and then you're supposed to use a different software. That's sometimes difficult if it's very complex projects, because there are softwares which might not be able to do construction staging as SOFiSTiK does. So that is usually kind of a discussion. And now you will say, why was this project so important for this axis-based bridge design? Because it's a pure straight bridge. Yeah, that's only on the first glimpse. The problem is This project is a part of the high-speed rail, or an enlargement of the high-speed rail connection between Munich and Berlin, actually. So they try to cut down the traveling time, which is at the moment more than 6 hours. They're supposed to have cut it down to 4 hours in 2017 when this connection opens. So still some years to finish. And what we see here is one of the bridges crossing, let's say, an intermediate mountain region of Germany. For your orientation, maybe that's Nuremberg. A little bit to the south, there would be Munich somewhere here, and up there on the map we would have Berlin. So it's right in the center of Germany, and we have to cross a quite mountaining region, and we have a lot of valleys, so there's a lot of infrastructure projects and tunneling going on there. And this specific project, Massetal Railway Bridge, it's located here directly inside this very complicated region. And we will see in a second what is the specific thing. So some basic data: length of superstructure is almost 400 meters. With an arch of 165 meters with roughly 40 meters height. Interesting is that we were supposed, or the bridge was supposed to be incrementally launched. Now we say, okay, no problems about a straight incrementally launched bridge. So they chose the construction method to be a post-tangent box girder. And of course we have the standard design codes at that time in Germany, which is DIN Fachbericht, which is very close to Eurocode, and some additional regulations for the German Deutsche Bahn. So this is here, project references with courtesy of the checking engineer, and we supported this checking in late 2010, so it's quite some years, but it was the first project where we applied together with the colleagues the CABD technology. So now you see the real problem of the bridge. Due to the fact that it's a high-speed rail bridge, the elements, or the route alignment elements, are very straight, of course, because if high-speed trains, they don't like to go in small radius. So what we really have here is a bridge which is in a quite complex track alignment. So we see here the gray axis, which is the track, the railway track. It's a connection between a specific spiral element and a constantly curved arch. And we have then here, that's quite interesting, the red thing is the superstructure. So the idea was, in order to maintain the capability of having this bridge incrementally launched, we have to have a constant radius. And in order that these elements are very straight, we're approaching this spiral and radius element with one constant radius for the superstructure. So the superstructure is in a radius of 34 kilometers actually, so a very big radius, very big arch. But of course this is still generating some sort of eccentricity, which you see in a minute. Furthermore, we have to consider the eccentricity, of course, of the track towards the structural axis. And furthermore, we want to have a straight arch, right? Because the arch itself, it has to maintain, hopefully, normal forces and a lot of moments due to the incremental launching. So we don't want to stress him with additional curvature. That would be quite stupid. So the arch acts as a tangent somewhere in between, more or less, these elements. So this bridge is on the second glimpse, geometrically quite interesting one. Here you see the effects. So that's a section in the middle, more or less in the middle of the bridge. So what we see, what's happening is that we have the cross section, we have the axis of the superstructure. We do have a different track. So you see the track already has an eccentricity towards the center of gravity. You know, railway loads are quite high, so we want to check distortional effects and all this stuff. And furthermore, we have the eccentricity of these arch elements, so two sections here of the arch, which has another eccentricity, you see it here, towards the cross section of the superstructure. So we have quite an eccentricity of the train to the superstructure and furthermore to the arch. So what was done here, we modeled this superstructure, the box girder, with one master cross section. In this case it was possible. So what variables were introduced in this cross section? Of course we had varying web thicknesses, so towards the supports or the piers on the arch, we had some larger thickness in this region of the cross-section. We did this by having a variable, and this variable is another ingredient for this computer-aided bridge design concept. So you specify the axis, and then you have along the axis different variables, which are then evaluated during the generation of the mesh. So no need to predefine maybe 100 or maybe 50 cross-sections to have this interpolation. We just define this variability, and then during the meshing, the program generates this different cross-section. Of course, in this case, if we just have one section with this thickness here and then just a linear variation, you might be able to do it with 3 cross-sections and then maybe consider some construction stage modifications, but principally this was the idea here. And it's not shown here on this slide. It's very important to have or to consider the non-effective parts over the support. So we reduce the effectiveness of the slab of this box girder and sometimes also of the bottom slab. So we have quite complex variant non-effectiveness for bending stresses. And this can also be modeled using this parametric bridge design concept. So here you see 2 sections which were interpolated after the generation of the mesh. So no need for the engineer to predefine this. This program generates it. Same was done with the arch. The arch is having more or less 2 variabilities because the arch, I don't know whether you see it here, varies in the width and in the height. So towards the top of the arch, the whole cross-section gets smaller in order to maintain also a nice shape. And the color coding you see here is the construction stages of the arch. Then the information how these placements were organized. Here we see the start segment. So it required a lot of placements. So you might think about my 3 placement example before. Here you have, especially along this part of along the launching nose, you have at least 10 placements. So it starts with the start section, then the connection, then the first joint for the first step of the launching, and so on. So, but it's still a very easily readable linear list in your input. And it doesn't make your input too complex for you in order to use the tool. Then you see the final model here with the colors again showing the different groups. Then we have a little look at the tendon layout, because I did not speak too much about that due to the limited time. You see several tendons were grouped together. We have quite characteristic for a launching bridge. We need a very high centric pre-stress, because for the box girder, the most critical step mostly in launching is when the first element with the launching nose hits one of the first supports. And you will see that in a second when we look at the envelope. And of course, we have continuity pre-stress for the final situation. So we have this parabolic shaped tendons here in the webs. Here some pictures of the results. So one, there was the construction stage analysis using specific moving spring elements in order to maintain the contact over the piers of the superstructure. And below you see one very important picture. So an experienced bridge engineer will immediately want to see this shark-like moment, shark fin-like moment of the start segment of the bridge. And we will also check probably the moment of the arch here, because when the bridge is launched from here to there, the first approach here is quite critical, because we approach an asymmetric antisymmetric loading for the arch and generate the following moment envelope after superpositioning of these construction stage results. Finally, I found a current picture of the project. You see it is some weeks old. At the moment in Germany it's already beginning autumn and winter. So this is, at the moment it's almost finished, the project, so every important work is done. Lately there was a news in the radio that they're starting to build the track now on this high-speed railway connection. So one of these projects, I'm very happy to be able to show this here. Some more references before I stop. Thank you. Is this one to show a different construction method or construction material. This is a composite bridge with a quite high architectonic aspect. So they wanted to have a slender integral bridge it's, first of all, it's difficult because you have this integral bridge, so you have to prove that all these stiffnesses are more or less properly, that with creep and shrinkage, because it's a reinforced concrete steel composite bridge, that those do not induce too high forces. So the approach was to have a very slender as possible superstructure in order to make it soft, to not generate too high forces. And you see that here, to have these V-shaped supports in order to have also a slender superstructure. So we have less supports, or half of the supports in the bottom than we have supported points on the superstructure. So this was done by also modeling because it's in a constant curvature, but we want to optimize, we supported the engineer for the tender design to optimize the steel quantities. So we had a variable along these axes of the different girders in order to change the plate thicknesses of the girders, because that was a very high, of course, effort and money for the construction company. And furthermore, the focus here also on the substructure in order to model these piles properly and all interactions. This project is just started, so it's work in progress. I hope that they don't find any problems in the design, which we supported partially, but I'm very lucky that this will, hopeful that this will be a very successful project. A little bit bigger, actually, the currently biggest infrastructure project in Europe. It's now named Queensferry Crossing. Before it was called Fourth Replacement Crossing, so there was a competition about the project name. The nice thing about this reference project is that nearly everybody was involved. So whenever I show this as a reference, everybody is happy because everybody did something for this project. So we got a lot of big construction companies. I think even from Spain, Dragados is involved. Yeah, but as so contractor, the contractor is a fourth crossing bridge constructor, which consists of Dragados, Hochtief, and a local consultant or local construction company. And also the design was conveyed with Leonhard Andre, Ramboll, Grondmey, Giffords at that time. So a very, very big project. Very, I think. I just know three pylon cable stay bridges. One is Ting Khao in Hong Kong, and this one, very interesting, because if you know that two pylons are fine with the stiffness, the third pylon is a big problem. So Ting Khao in Hong Kong has these additional famous long cables, which look not so nice because we have this sag due to the length. And here we have this overlapping of cables, which is very characteristic. Another bridge project by Grassl, something for shell design, with some shell pre-stressing, very nice project in Vienna. And finally, that was my talk. So I'm not sure whether we will allow for some questions, but otherwise we just continue with Dimitri, and I thank you for your attention.
Спасибо большое, Штефан. Да, к сожалению, опять не остается времени на вопросы. Но напоминаю, что у нас есть возможность задавать вопросы во время кофе-брейков с помощью нашего переводчика.